going to do pretty much the same thing as we did in example 2, except we're going to have odd exponents. And once again, tomorrow we'll talk about the reasoning why this works. But when you have an odd exponent, you're going to do things differently than with an even, because we can't just cut 9 in half. We're going to end up with a decimal, and we don't want decimals as part of our answer. So to start this out, I'm going to work with the square root of 27. The square root of 27 would break down into the square root of 9 times the square root of 3. Because 9 is the biggest perfect square that will go into it. The square root of 9 is 3. We're going to leave a little bit of space again, and then bring down our square root 3. Now the shortcut when you're working with an odd exponent is to borrow 1. So instead of a to the 9th, I'm going to make it a to the 8th. I'm going to make it an even exponent. But the one that you borrow, so I borrowed an a, and I can't just forget about that, so I have to bring it down and put it under the radical sign. So this would be the one that I borrowed. Now I can take the square root of a to the 8th now because it's an even exponent, and I would cut it in half, and 8 divided by 2 is 4, so a to the 4th would come on the outside. So your answer for this one would be 3a to the 4th times the square root of 3a. If we try another one with an odd exponent, we'll worry about the exponent in a minute. Let's break down our 60. Oops. Change our color. Okay, if we look for the largest perfect square that goes into 60, it would be 4. So this would be the square root of 4 times the square root of 15. The square root of 4 is 2, so that comes on the outside. Our 15 stays under the radical. And now we have to deal with our exponent, and our exponent is an odd exponent. So we're going to borrow 1 and make it a 10. But the one that we borrow has to go under the radical sign. So the t that we borrowed comes after the 15. Now we can take the square root of t to the 10th by cutting it in half or dividing by 2. And 10 divided by 2 is 5. So t to the 5th power comes on the outside. So our answer would be 2t to the 5th times the square root of 15t. In example 4, which is our last example, we're simplifying and we're kind of putting it all together. So we've got even exponents, we've got odd exponents, we've got numbers, variables, and exponents on the outside of the square root. So if we look at this particular problem, I always work with my number that's under the radical first. So the very first thing I want to do is try to break down 72. And the biggest perfect square that goes into 72 is 36. So it's the square root of 36 times the square root of 2. The square root of 36 is 6. But remember, you have to multiply that by what's on the outside. So I'm going to take 6 times 4, which is 24. I'm going to leave quite a bit of space because I have 2 variables. And root 2 can be brought down. Okay, now I have to work with my exponents that are underneath the radical. Since I have a to the 7th, and 7 is an odd, I'm going to borrow 1 and make it a 6. Now the one that I borrowed has to go under the radical. So the a that I borrowed goes under the radical. Now to get the square root of a to the 6, I divide it by 2, which is a to the 3rd. But I have to remember, since I have a's on the outside of the radical, I have to combine them together. And if I take a to the 3rd times a to the 3rd, remember your rules, it actually becomes a to the 6th because you add your exponents together. And now I'm going to work with my b's. b to the 10th, well 10 is an even exponent, so I just divide it by 2. And if I take the square root of b to the 10th, it becomes b to the 5th. And there's already a b on the outside of the radical, so I'm going to multiply those together. And this has an imaginary 1 as an exponent, and b to the 5th times b would be b to the 6th. So our final answer for that problem is 24a to the 6th, b to the 6th, times the square root of 2a.